This is going to be the fifth section of the fifth chapter of stats. This is going to be on the Poisson probability distribution. So we've been over this stuff about binomial probability distribution in the last two videos, and so now we're going to look at another type of probability distribution, which is called a Poisson distribution. So it's a discrete probability distribution that applies to occurrences over some interval. So what the heck does that mean? Basically, it's about the number of times something occurs over a set period of time or distance or some sort of set period of um, measurement. So it's a little bit different than a binomial distribution. So if you remember, a binomial distribution is basically how many successes you get out of X number of tries. So it's you have a set number of tries that you're going to take, and you're recording how many successes you get out of that. Poisson is like saying, okay, you have a set chance to succeed. How many occurrences are you going to have over 5 minutes? So it's not really how many tries per se, it's how much length of time, or even in some cases distance, do you have to make an attempt on. So again, this could be a distance, it could be time, it could be area, it could be volume, it could be space, it could be anything that you can kind of put into an interval that you're tracking over. So the formula to get the probability of a Poisson distribution is this here. The little mu symbol here, Greek letter mu, is the average, and then the um, sigma here is the standard deviation. And so we'll get into that a little bit here in a second. You might not see it up there, but there's a reason for that. So again, this will come back later, but right now just make sure you remember that the mu here is the average number of, or basically your average expected value. And again, this will make sense when we get into an example here. So it sounds kind of cryptic here. Just stick with me. So some requirements first before I go over how to use it. It's basically the same requirement as a binomial. So if you remember the requirements for binomial, it's almost the same cases here. So just think it requires the same things as a binomial for the most part. Now, what about the difference? So as I said before, the main difference between a Poisson and a binomial distribution is a binomial distribution tracks how many successes out of a certain number of tries. So for a binomial, you have a set number of tries, and you want to figure out how many successes are you going to get off those. For a Poisson, you have a set distance or a set area or a set space, and you want to figure out how many occurrences do you have within that set space or set time frame. So you're not trying a set number of tries, you're measuring over a set number of times. So it's like saying, this is kind of a poor example because it kind of walks the border of both there, but it's like saying you're going to shoot 10 free throws, and you want to figure out how many successes are you going to, what's the chance that you'd get. Let me write down here actually, rather than just talking about it, that'd make more sense. So a binomial, I'll put B here for binomial. A binomial would be something like you have 10 free throws, and you want to figure out what's the probability that you make 5 of them. So if you shoot 10 free throws, what's the probability you make 5 of them? That'd be a binomial. A Poisson would be like you make as many free throws as, or you shoot as many free throws as you can over 1 minute. What is the probability that you get 5 of them? So in this case, you're making 10 free throws, no more, no less. In this case, you're simply shooting as much as you can in 1 minute, and you want the probability that you make 5 of those free throws. And again, this kind of walks the line there because even over 1 minute, you can count how many tries you made. But that's kind of the overall difference if you look at the bigger scope of things, is that binomial is a set number of predetermined tries, whereas Poisson is basically how many can you fit in this time span or this distance span. So some history here. This is actually a famous example of the Poisson distribution. It was actually, again, this is a historical example here, so it was actually used. The British military wants to find out if the Germans here during the World War were targeting certain installations. So they were getting bombed, obviously, and they want to figure out, okay, are they bombing just randomly, or are they bombing to try to find some bases, or do they know something that we don't know that they know, and we need to adjust here. So again, obviously, if they're bombing over a certain area, some areas are going to get hit more than others, but they wanted to know, is this just random chance that some areas got hit more, or are they hitting some areas more by intention because they think something's there? So here's the data that they got. They took their space there. They took South London and they divided it into 576 regions. So they took a map of South London, split it into 576 regions with a uniform square area, so 0.25 kilometer square area. And they counted that a total of 535 bombs hit the area um, of that 576 regions. So think about, like, obviously South London isn't a perfect square, but think about if this is South London, put SL here for South London. They divided it into 576 squares, and they found that out of these areas here, 535 of them were hit. So again, it could be hit right in the center, it could be hit off the corner, we don't know, but of these regions here, of those 576, 535 of them were actually hit. So given that there are 535 bombs dropped, what is the probability that a given region is going to be hit twice? So what's the probability that they're going to hit this region right here twice? Right, what's that chance? Now again, we have a set space here, 576 regions, each with a square kilometer rating of 0.25. So we have a set area, and we want to drop these bombs randomly, quote unquote, and figure out what's the chance that a certain area, any area here, gets hit twice. So we're not doing a set number of tries, even though you might think, well, if we're dropping 535 bombs, isn't that a set number of tries? Not exactly, no, because the key thing here is that you're dropping them over this area. So it's like you're dropping them all at once. Think about it like that. You're dropping those bombs all at once, and you're trying to figure out where would they land, and what's the chance that two of them landed in the same spot. Think about it kind of like that if you want. So to find the Poisson, remember the only thing we need for a Poisson is the average. So if you look back at our formula, whereas for a binomial, remember for a binomial we needed n, p, and q for a binomial. For a Poisson, all we need is the average, because the x is what we decide to check for. So in our case, x would be 2, because we want to figure out what's the chance that a region gets hit twice. But as for the actual number we need from the data, all it is the average. Once we get the average, then we're good. So if we're going to drop 535 bombs over 576 regions, we expect each region to get hit 0.929 times. Now, obviously, a region can't get hit 0.9 of a time, but that would be the average number we would expect to happen, is that each region would get hit 0.929 times. So now that we know the average, we can figure out the chance that a region gets hit twice. So we go to our formula here. So x is 2. So we have the average number, which is 0.929, to the x power, which is 2, times e to the x power, and that divided by x factorial. So if you plug it in here, you end up getting 0.17. So the chance that a region gets hit twice is about a 17% chance. So it's not all that unlikely that a region gets hit twice there. Now, obviously doing that can take some time to do. So luckily our calculator has a Poisson formula shortcut for us. So much like the binomial, we go to second vars, go down past the binomes PDF and CDF, and we go to Poisson. So you can see that there's a Poisson PDF and a Poisson CDF, and they work the exact same way as a binomial. PDF is for exactly a certain number of successes. CDF is for a cumulative number of successes. So if you want to figure out what's the chance that a particular region gets hit at most 2 times, then you would use Poisson CDF, because Poisson CDF would calculate the chance that it gets hit 0, 1, and 2 times, and then adds them all together. So CDF is when you want a range of probabilities. PDF is when you have an exact probability you're checking for. So in our case, it would be PDF. You type in the average first, so 0.929, comma. Then you type in the number of successes you want, which in this case is 2. One region get hit twice. And you get your answer there, 0.170. So again, that's how all Poisson problems go. They're actually much easier than binomial because all you need is the average. And remember, you get the average, so I should probably put that here. To get the average of a Poisson distribution, all it is number of total. So this could be total space, could be total time, could be total area, but number of total over a number of tries. So in our case, number of total was 576 because we had a total of 576 areas, and our number of tries was 535, I believe, right? Yeah, 535 because we had 535 bombs being dropped. So that's how you get the average, number of tries over number of total, and then all you do is plug it into your calculator and go. So we can also do this again for 0, 1, 2, 3, and 4, and then add them together, or we can use the CDF to get that. So again, binom, or sorry, I should say Poisson. So Poisson CDF, I'll just abbreviate it here, Poisson CDF. If I type this in to 9, 5, if I type that in, that would give me the probability of getting hit between 0 and 5 times. So this would give me the probability of a region getting hit up to and including 5 times. If I wanted it to be the probability of getting hit 6 or more, I would take 1 minus this, because 1 minus this would be the probability of getting hit 6 or more times. And you, unfortunately for a binomial, you can't instantly create a table, but you can do this manually and get a table yourself. So for example, you can go Poisson PDF, and you can physically type in 1 or 0, then you can type in 1, and then you can type in 2, 3, 4, and you can get these values yourself and make your own table. It's a little bit longer, but you could technically do it. So let's do some more here just to make sure we get the idea. I'm not going to necessarily do all these, but just to give you the idea and make sure remember the button prices there. So if I want the probability using the same information, so we're going to use the same information, so average is 0.929. If I want the probability of getting hit 0 times, I would go to second vars, Poisson PDF, type in my average, 0.929, comma, and then type in how many times do I want to get hit? Well, 0. So what's the chance that our region doesn't get hit at all? Well, about a 39% chance, 0.395. 0.395. So about a 39 or 40% chance that a space does not get hit at all. Which, again, if you're in South London at the time, that's somewhat encouraging at least, that there's a 40% chance that your area is not going to get hit at all, but probably still scary. We already did 2. Let me change one of these up here. So instead of doing probability 3, what if I said the probability of at most 3? So what's the chance that a region gets hit 0, 1, 2, or 3 times? Well, if I want that, I would go to math. No, sorry, I go to second vars, so that's what I'm doing. Go to Poisson CDF, type in my average, comma, I want to get hit at most 3 times, so type in 3. And I get about a 98.5% chance. 0.985. So the probability that your region gets hit at most 3 times, the probability that you get hit 0, 1, 2, or 3 times is about an 80, 98, 99% chance that that happens. Which again is almost certainly likely. So we can say that you're almost certain to get hit at most 3, or I guess you could phrase it if you want to be a little bit more positive, you'd say we're almost certain that you get hit no more than 3 times. So if you've gotten hit 3 times, chances are you're probably not going to get hit another if they're bombing randomly. Now, if one space got hit, 5 times, we'd say, okay, well, the probability that we get hit at most 3 times is almost 100%. So the chance that they're just bombing randomly and the space just got hit 5 times by random chance is not likely. So they're probably searching for something in that space. So they probably think that there's something there in that space, and maybe there is, and we need to pull out, that sort of stuff. So that's how they would use this information to kind of gauge whether they're simply being bombed randomly or whether the Germans are looking for something and they need to move something away. Last one here. Let's do this one here, but I'm going to change this one up too. I want the probability of getting hit at least 4 times. So I want the probability of getting hit 4 or more, essentially. So when I say at least 4, that means 4 or more. Okay, well, I could do that. I would go second vars, Poisson CDF, because I want an at most or at least number. So Poisson, come on, Poisson CDF. Same information, excuse me, got a hiccup there. 929, comma, and I would still put in 3. So why 3 and not 4? Remember, if I put in the 3 here, CDF gives me everything from 0 up to and including 3, which as we know is 0.985. So what I would do is I would take 1 minus that 0.985, which would end up being 0.015. And that would be the probability of getting hit at least 4 times. Because if this is the probability of getting hit 0 to 3 times, if I take 1 away from that, that means that everything past 3 is what I have left, which is 4 or more. So when you're doing the at least number, you should always type in the CDF version of 1 less than your maximum or minimum. So if you want at least 4, 1 less than 4 is 3. So you do the CDF of 3 and then take 1 minus it. So think of at least, you should have a subtraction there. That's where that 1 minus comes from. Whereas if you want at most, it's just simply CDF of that number and you're good. And then obviously if you want an exact value like 0 or 2, you would use the PDF version. So that's it for this video. Hopefully it helped you out. Again, Poisson, once you get used to it, is actually much easier than binomial because all you need is the average number, whereas binomial you need the n, p, and q. But as always, let me know if you have any questions. Till then, thank you for watching and have a good day, night, or afternoon.